just mentioned the concept of divisibility. A number divides another, and the greatest common divisor, that's basic. Then we said we introduced maybe something you don't know about, relatively prime. Two integers are relatively prime if their greatest common divisor are 1. Prime numbers, you know about prime numbers, and maybe you don't know that any integer can be factored into primes. Let's give an example of that, just to illustrate that notation that we have there. For example, using this notation here, the value 3,600 is the prime factors of 3,600. 2 to the power of 4, 2 is a prime number, 3 squared times 5 squared. That is, 2, 3 and 5 are the prime factors of 3,600. What have we got? Here. Yes, what have we got? This should be P1. Good point, pick up. The general format of some integer A, if we write it as a factor of its prime numbers, that is the prime number to some power, and for each prime number that we know of. So here, for example, 3,600 is simply 2 to the power of 4 times 3 squared times 5 squared, where we would say A2, if P2 equals 2, A2 is 4, A3 is 2, A5 is 2. So just some notation that you may see in the textbook. But the main point is that we can factor any integer into primes. It's not easy sometimes with very large numbers, but we can in theory. What else do we see? Some prime numbers. And then we introduce modular arithmetic. We do our normal arithmetic, but in mod n, with some modulus. Everything is performed within a set Zn when it's in mod n, so from 0 up to n minus 1. The rules for ordinary or normal arithmetic for addition, subtraction and multiplication also apply for modular arithmetic. We're not going to go through all those rules, but another example. What I put equals there. It's been a long day. 11 to the power of 7 mod 13. What's the answer? Your quiz next week, if I give you that, you don't have your calculator.
We can use calculator.
Not with this one. How do you solve it? Even if you could, it'll take you some time, because 11 to the power of 7 is, I know, several, I checked before, 15 million or something like that, several million. So some strange number, mod 13. 711. We have 711s multiplied by each other. That's what 11 to the power of 7 is. 11 times 11 times 11 times 11. And we... The answer is 10?
No. 14.
Let's try and expand it. And we'll use this property. Exponential is just multiplication, 11 times 11 and so on. So we can use this property, that is A times B mod n, we can rewrite as A mod n times B mod n, all mod n. So 11 to the power of 7, we can also write as, we can do it different ways, 11 squared times 11 squared times 11, all mod n, mod 13 in our case. So it's just an expansion of 11 to the power of 7 is the same as 11 squared times 11 squared times 11 squared times 11, which is also the same as 11 squared to the power of 3. 11 squared to the power of 3. We've got 3 of them. And we can essentially bring the mod inside the brackets, as we do here. A times B mod n, bring the mod inside at A mod n times B mod n, all mod n. So let's bring that in. Actually, use all mod n, mod 13. So that's just using the property that we have there. Bring the modulus inside. The first step was simply expanding the exponential. Why do I expand it in that way? To make it a little bit easier in solving.
I think no power to here.
Ah, sorry. No power to the 2 there. Any other mistakes? There's 3 11 squared and 1 11 to the power of 1 here. Just 11. Okay, good. What's 11 squared? 121. And we can even bring this mod 13 in again. (11 mod 13) is 11. This part here. So all I did is 11 squared is 121 here. And also I bring the mod 13 inside there using the same principle as before. And I solve this. 11 mod 13 is 11. Just to make the steps a bit simpler. What's 121 mod 13? 4. So you could work that out in your head. You don't need a calculator. 130 is 10 times 13. 130 minus 121 is 9. So we have 4, a remainder of 4. 121 mod 13 is 4. Four cubed mod 13. 4 cubed is 64 mod 13. 64, 4 cubed is 64, mod 13 is 12. So this becomes 12 times 11. Twelve times 11. 12 times 11 is 132, mod 13 is 2, because 130 is 10 times 13, remainder 2. We have our answer. It demonstrates that we can take this seemingly complex calculation. 11 to the power of 7 is something like 10 million, mod 13. Try and do that manually. It will take you a long time. Expanding, we can get the answer relatively simply, using very basic mathematics. And importantly, your computer can do that fast. Instead of 11 to the power of 7, maybe a large number to the power of a large number. 10,000 to the power of 40,000. So your calculator will not solve it for you. But using these principles, you can break it down into the steps and make it a much simpler problem. Just a demonstration of one of those rules. If you didn't follow that, then go back and check. It's not applying anything that you don't know, that you haven't learned probably in high school. We introduced that in modular arithmetic, we think of a subtraction as adding the additive inverse, where the additive inverse of some number, the additive inverse of b, is the number that when we add to b, we get 0 in mod n. Similar with multiplication and division, we have a multiplicative inverse. And we perform division by dividing by the multiplicative by multiplying by the multiplicative inverse. The multiplicative inverse, when we times two numbers together and get 1 mod n. All integers have an additive inverse. Not all integers have a multiplicative inverse. Only if the integer and mod n are relatively prime. Fermat's theorem. So this is a theorem that applies in modular arithmetic. We're not going to attempt or try to derive it. The theorem has two variations. First one, if p is a prime and a is a positive integer not divisible by p, then this is true. Who did not submit the assignment? I've marked the assignments, or I've checked the assignments. I haven't got all the marks yet. But I think there were 4 or 5 students who it did not decrypt. Most people it decrypted fine, so that was okay. But there were some people it did not decrypt. So they have some problems. And I asked them to send me emails. You sent me an email, that's fine, that's okay. Yours? Did I ask you to send me an email? No, yeah. I think no one here. You sent me an email, yours was okay. Yours was okay, well, I found the error in it. So some people made errors. They used the key, they used minus k with lowercase k. There's a difference between uppercase k in OpenSSL and lowercase k. Uppercase k, you specify the actual key. Lowercase k, you can specify a password and it will generate a key. So it makes a difference there. Some people use the wrong, a non-random key, but they didn't lose marks for that. I think everyone else here was okay. Fermat's theorem. not on the website yet, but I've put a video of me generating the ciphertext and decrypting the ciphertext, including generating the random key. So if you did not create a random key, you can look at that video and see how you can generate a random key as an example. And the marks will be in a day or two. Fermat's theorem. A to the power of p minus 1 is equivalent to 1 in mod p. And a variation of that, if p is prime and a is some positive integer, a to the power of p is equivalent to a, mod p. We can see the relationship between them. A to the power of p minus 1, if this is true, and we multiply by another a, both sides, multiply 1 by a and you get a, multiply a times p to the minus 1 by a and you get a to the p. But you may see both variants of that theorem. It's useful in some of our ciphers. We're not going to derive it, we'll just demonstrate that it holds. That's simple values. Well, what do we need? We don't need that. What's the answer? Too slow. Look at the theorem. A to the power of p minus 1 mod p equals 1. Some integer to the power of p minus 1, if p equals 5, p minus 1 is 4, then the theorem should hold. It has the format of this side, this. See, if p is 5, then it becomes 3 to the power of p minus 1 mod p. And Fermat's theorem says a to the power of some integer, 3 in our case, to the power of p minus 1 mod p is 1. So we immediately know the answer is 1 here. It's an example of how we can use it. Okay. Answer? 3. We see has the format of the second variation of the theorem. A is 3, p, our prime, is 5, mod 5, integer to the power of 5, mod 5 equals that integer, 3. All right, these are simple examples where I've used small numbers, but if you have larger numbers, then rather than trying to solve it manually, going through the steps, you can, if it matches the format of this theorem, you can quickly find the answer. One more. Answer? 1. It doesn't match the theorem. P is not prime. So be careful if P is a prime. So here we'd need to manually work it out, and it turns out it's 1, but not because of the theorem. So be careful. P must be a prime number there. So there are conditions. We'll see that in play shortly. Euler's theorem. And to introduce that, we need to first explain Euler's totient function. Euler's totient function is the number of positive integers less than n and relatively prime to n. So some number n, we look at all the integers that are less than it and count the ones which are relatively prime with n. Some examples. And then we'll introduce Euler's theorem. That's some good examples somewhere. The totient, or Euler's totient of 5. What is it? Answer is 4. There's a shortcut, but let's go through the long way first. That is, the answer is all the integers which are less than 5, so of 1, 2, 3 and 4, and the count of those, that is the number of them that are relatively prime with 5. Let's say, are 1 and 5 relatively prime? Yes, because the greatest common divisor of 1 and 5 is 1. So they are relatively prime. 2 and 5, also relatively prime because, again, greatest common divisor of 1. 3 and 5? 4 and 5? Relatively prime. There are 4 integers less than 5 which are relatively prime with 5. So the answer here is 4. The totient of 6. Okay, let's confirm, just go through the manual step. 1 and 6, relatively prime. There's 1. 2 and 6? No, 2 and 6 have a greatest common divisor of 2, not 1. So 2 and 6 are not relatively prime. 3 and 6? No. 4 and 6? No. 5 and 6? Yes. 1 and 6 and 5 and 6 are relatively prime. Therefore, the answer is 2. So that's the definition of Euler's totient function. Count the number of numbers less than n which are relatively prime with n. There are some shortcuts. By definition, the totient of 1 is 1. That's one thing. For a prime number, if n is prime, then the totient of a prime number is p minus 1. The totient of a prime p is p minus 1. As we see here, 5 is prime, the totient is 4, that is 5 minus 1. Because all the numbers less than that prime number need to be relatively prime with it, by definition. So take any prime number, you can quickly calculate the totient of that. If it's not prime, then you need some algorithm to go through and calculate. Totient of 19 is 18, because 19 is a prime number. We have another shortcut, and we make use of this shortcut in one of our ciphers. If we have two prime numbers, P and Q, and multiply them together to get n, then the totient of n is P minus 1 times Q minus 1, or the totient of n, if this condition holds, that is 2 primes P and Q, n equals P times Q, then the totient of n is the totient of the 2 primes multiplied together. Which is totient of P, because P is prime, is P minus 1, and the totient of Q, because Q is also prime, is Q minus 1. We see that's a very useful rule or a shortcut when it comes to RSA. So that's the quick definition of the totient function, Euler's totient function. And then it's used in Euler's theorem. Again, we have two variations of how it's stated, the same concept. For every a and n that are relatively prime, a to the power of the totient of n is equivalent to 1 in mod n. And a variation of that for all positive integers a and n, a to the power of the totient of n plus 1 equals a mod n. So that's just the statement of Euler's theorem. Some quick examples before we get to the hard stuff. Let's get a better example. What's a to the 1024 mod 11? It's a bit too easy to solve that one, but let's use the Euler's theorem to solve it. We could solve it manually and find the answer, but 1024 2 to the power of 10. How does that help us? Let's try Euler's theorem. There's different ways to solve this, probably easier than the one we're going to use. You can use your calculator. Let's see how Euler's theorem helps us. Next time I'll give you larger numbers. N is 11, our modulus. What's the totient of 11? (11) is a prime number, therefore the totient of 11 is 10. So this has the format of our theorem here. That is, we have 2 to the power of the totient of 11 mod 11. 2 to the power of the totient of 11, which is 10, mod 11, matches what we have here. A to the power of the totient of n, mod n, equals 1. This is just using Euler's theorem there to solve that calculation. solve that problem. Again, when you're dealing with larger numbers, the direct solving is maybe takes too long, then applying the theorem can get the answer quickly. So you're not going to have to derive these theorems, though usually are stated and given. Understand the totient function, how to find an answer for that. We'll say a little bit more about its complexity later. Last set of operations in modular arithmetic, we've done addition, subtraction, multiplication, division. We have exponentiation and logarithms. Exponentiation is simply repeated multiplication, so our same principles apply. We can do exponentiation easy. What about logarithms? So with exponentiation, where we raise something to the power, we can solve that using our normal arithmetic, but mod n. But with logarithms, which are the inverse operation, because exponentiation is really just repeated multiplications, logarithms related to division, but remember with division, we had a problem. Not all numbers have a multiplicative inverse. And that similar problem follows through for logarithms. So let's first define it. This is just using ordinary arithmetic. If b equals a to the power of I, then I, the index, or the exponent, equals log in base a of b. That's a logarithm in ordinary arithmetic. In modular arithmetic, we have the modulus as well. If b equals a to the power of I mod p, then I equals the logarithm in base a mod p of b. So we've just introduced this mod p, and when we write down the logarithm, we include the p as a second parameter here. And logarithms in modular arithmetic are called discrete logarithms. So you'll sometimes see it written as d-log for discrete logarithm, to distinguish. So this is the way to write the discrete logarithm. As with multiplication, where there's not always a multiplicative inverse, we cannot always do a discrete logarithm. There are only certain conditions. That is, we cannot always find a unique value of I. We can find a unique exponent I if a, the base, is a primitive root of p, of a prime p. So p, mod p, if p is prime and the base a is a primitive root of p, then there's a unique value of I. So to understand this, we need to explain what is a primitive root. If a is a primitive root of p, then it holds that a to the power of 1 mod p gives some answer. A squared to the a to the power of 2 mod p gives some other answer. And a all up to a to the power of p minus 1 gives some answer. And of all those answers, they are distinct. That is, they're different values. If that's true, then a is a primitive root of p. Let's give some simple examples to see a primitive root. Test some values. let's choose a prime p equal to 7. And let's choose a equal to 3. And let's try all these cases. That is, what is 3 to the power of 1 mod 7, 3 to the power of 2 mod 7, and so on. And look at the answers. First, what's 3 to the power of 1 mod 7? 3 mod 7. 3 squared mod 7. 3 squared is 9, mod 7 is 2. 3 cubed mod 7. 27 mod 7. 6. 3 cubed is 27, mod 7. 6. 3 to the power of 4 is what? 4, is it? I don't know. I won't ask you to do them all. I've got the answers. Three to the 4 mod 7, 4. 3 to the 5 mod 7, turns out you can use your calculator, is 5. And 3 to the power of 6 mod 7 is 1. Therefore, A is a primitive root of P. 3 is a primitive root of 7 in this case. Why? Because 3 to the integer exponents, mod 7, gives us distinct numbers here. They're all different. 1, 2, 3, 4, 5, 6. If that's true, then it's a primitive root. And if A is a primitive root of P, then we can solve a discrete log. If discrete log of A, base A, that is 3, mod P, P is 7, of some number, and we'll get an answer. What's the discrete log of 6? Think about that. This discrete log in base 3 mod 7 of 6. Two is wrong. Go back to our normal understanding of logarithms. What's the logarithm of some number b? Well, the answer is the exponent. If we take a to the power of some number, we shall get b. Same here. If we take a, our base, 3, to the power of some number, and mod by p now, we have mod p, equals 6, and the answer is 3. And we have it here. So this is what we need to solve. We need to find the value of the question mark there, because the discrete log says that if we take 3 to the power of some number, mod it by 7, we shall get 6. You can trial and error, but we've calculated before, in fact, that the number is 3. Three to the power of 3 mod 7 is 6. problems? Can we use 10? We're in mod 7, so 10 will be 3. All our answers, we're operating within the set of Z7. That is, everything, all our answers really need to be in 0 to 6. If we use 10, then we'd need to mod that first. So in modular arithmetic, we deal within the confines of some set, dependent upon the modulus. Only some, or the only integers that have primitive roots, 2, 4, any prime number that is odd to the power of some integer, alpha, some integer, or 2 times that prime number to some integer. So that's just the set of integers that have primitive roots. Some prime number to the power of 1, to the power of 2, to the power of 3, or 2 times that prime number to the power of 1, 2, 3, and so on. So not all integers have primitive roots. And if we cannot find a primitive root, then we cannot solve the discrete logarithm. Another example. Another example is on the slides. Here in this example, it's mod 19. So what this slide shows is that for different values, a from 1 to 18, here is the answer when we take a to the power of 1, mod 19. The second column is a to the power of 2, mod 19. The last column is a to the power of 18, mod 19. For example, let's take the last row. If a is 18, then 18 mod 19 is 18. 18 squared mod 19 is 1. 18 cubed mod 19 is 18. They've calculated it for us. We don't have to do that. 18 to the power of 18 mod 19 turns out to be 1. That's all it's showing here. So we see the primitive roots of 19. It's all these values of a which give us distinct values along the row. There are 6 primitive roots. 2, 3, 10, 13, 14 and 15. Because with 2, if a is 2, 2 mod 19 is 2. 2 squared mod 19 is, wake up, 2 squared mod 19 is 4. 2 cubed mod 19 is 8. 2 to the power of 4 mod 19 is 16. 2 to the power of 5 mod 19. So 32 mod 19 is 13. 64 mod 19 is 7. We keep going. 2 to the power of 18 mod 19 is 1. Look at this row. The numbers are distinct. They're all different. They are the values 1 to 18. Therefore, a or 2 is a primitive root of 19. And we also see 3 is a primitive root of 19, 10, 13, 14 and 15 are primitive roots. So that's just found out the primitive roots. That means we can solve discrete logarithms, mod 19, if the base is one of those values. And the answers for those discrete logarithms are listed here. That is, we had 6 primitive roots, 2, 3, 10, 13, 14 and 15. So if we take discrete log, it doesn't show the d here, discrete log in base 2 mod 19 of some number, if that number is 1, then the answer is 18. If that number is 18, the answer is 9. So it's worked it out for us. We could do them manually. It would take some time. But it shows that in mod 19, there are 6 bases that are primitive roots, and therefore 6 bases which the discrete log can be solved for. The other bases, 1, 4, 5, 6, 7, 8, 9, and so on, we cannot solve the discrete logarithm for. There's no unique answer. We will use that when we do a key exchange with Diffie-Hellman key exchange, the discrete logarithm. So we've gone through modular arithmetic, the 6 operations: addition, subtraction, multiplication, division, exponentiation, and logarithm, or discrete logarithm. We've introduced 2 theorems, including Euler's totient function, and we see discrete logarithms can only be solved when the base is a primitive root of the modulus, and the modulus is a prime p. Everyone's okay to move on? So that's getting more new concepts. Last slide here. Some problems related to number theory are complex, computationally hard. That means if the numbers are large enough, no one can solve them in reasonable time. So that is similar to our brute force attack. A computer cannot solve the problem within thousands or millions of years. That's what we define as computationally hard. There's no known way to solve it at the moment. Some of those problems which are computationally hard, which related to what we've just discussed, integer factorization. That is, if there are 2 unknown primes, p and q, and n equals p times q, I'll give you n. It's hard for you to find p and q if they are large enough numbers. There is no known algorithm to find p and q in reasonable time. So if I choose a prime p, a large number, maybe 1,000 bits, and another prime q, which is equally as long, I multiply them together and get n. Then I give you n, you will not be able to find p and q. There is a p and q that satisfies the equation, but it would take too long to solve it, to find. We will see that this principle is used in the next cipher, RSA. Some competition has been held over the past few years, or maybe 5 years ago, of how large a number can someone factor? How large an n can someone find the prime factors for? And the largest one that was, this may be 1 or 2 years old now, the largest one was a value of n which had 768 bits, or 232 decimal digits. So you write a number with 232 digits, then that's about the limit that someone could factor into the prime numbers. Any larger, and it takes too long. So if you have 1,000 bits, then it's going to take too long for someone to find the prime factors. Another problem which is computationally hard is Euler's totient. Given some value n, non-prime, a composite value of n, it's not prime, find the totient of n. It's computationally hard. That is, if n is large enough, again, a very large number, then if n is not a prime number, then it will take you forever to solve it, to find the totient of n. And it turns out that it will take longer for equivalent sized numbers than integer factorization. That is, this is harder than this problem. Because as we see, what's the totient of 34? 34 is not prime, so you need an algorithm to go through and find all the numbers less than 34 relatively prime with 34. All right, you can do that for 34. Now take a 300-digit number and find all the numbers less than that, which are relatively prime with that, and that's unsolvable in reasonable time. So finding the totient of some number n which is not prime is hard. Finally, finding the answer of discrete logarithms is computationally hard. If you know a and p, the base a, the modulus p, and b, find I. Then again, if the numbers are large enough, finding out I will take too long. Cannot be solved. That is, it's about, in terms of difficulty, it's about the same as integer factorization. These are considered computationally hard, and our ciphers will take advantage of these problems. Advantage of the fact that going in one direction is easy. Calculating the exponent, multiplying two numbers together is easy. Going in the other direction, taking this number n and finding the two factors is hard. So that's what our ciphers will take advantage of. Any questions before we move on to the public key cryptography and see these in play? Any questions? Any questions on anything? Preferably on this lecture.
Will there be lots of calculation in the midterm exam?
Again?
Will there be lots of calculation on?
Will there be lots of calculations in the midterm exam? Some, yes. There'll be some simple calculations on number theory, but normally those calculations will be applied to the ciphers we're about to go through. So yes, there will be some. In any exam, midterm and final, you're allowed to have your calculator. But you'll find that there may be questions which your calculator cannot solve. That is, although we don't have it, when we take some number and raise to a large power, your calculator won't get the answer. It's too large. But you can apply some of the rules to break it down and find the answer. We're going to introduce the concept of public key cryptography. I don't know if we'll get a chance to go through the details of the next cipher, but we'll introduce the concept today. What we've covered up to now with our example ciphers were symmetric key ciphers. Both the sender and receiver needed to know the same key, and it needed to be a secret key. So it's called symmetric key or secret key. What else? Shared key cryptography. Now we're looking at something different, public key cryptography, where we'll see that there are two different keys. One of them will be public, made known to anyone, including attackers. Let's look at the principles of how public key crypto systems work. Pretty much up until the 1960s and 70s, all ciphers were using symmetric key cryptography. Caesar cipher was symmetric key. You needed to know the shift that we used. Des, symmetric key. In the 60s and 70s, people initially secretly went to work on some variations, public key cryptography. The first public introduction of public key cryptography was in 1976 by Diffie and Hellman. The idea, their motivation was to make it easy to exchange keys and to avoid the reliance on other entities for exchanging keys, key distribution, and to allow other things like digital signatures. That is, with secret key or symmetric key cryptography, if I want to send something to you, I need to first exchange keys. All right, if you want to do that on a large basis with many users, a practical way of doing that is having a central authority who distributes keys on your behalf. For that, you need to trust that central authority, like a government. So they wanted an approach that didn't rely on this central authority, that the users themselves could conveniently exchange the keys. So that, it turned out, they come up with a system where one key is public, I just yell it out, everyone hears it, but I have a corresponding private key, and using the right algorithms, you can still securely communicate with me. So that was the motivation of Diffie and Hellman. They produced their algorithm. We'll see the Diffie-Hellman algorithm for key distribution shortly, or not today, next week. It turned out before that the NSA in the US and in the UK, a government cryptography group were working on the same principles. They just did not publicly reveal that until later. So this type of cryptography is quite new compared to the Caesar cipher, which is 1,000 years, so hundreds of years. Symmetric key algorithms use the same secret key for encryption and decryption. Asymmetric algorithms use one key for encryption and a different key for decryption. But the two keys must be related in some way. The requirements for asymmetric algorithms to work is that it must be computationally hard to work out the decryption key from the encryption key. Because one key is going to be public, everyone knows it, if you can work out the other key from the public key, then it will not work. One key needs to be public, one needs to be private or secret. So it needs to be computationally infeasible or hard to derive one key from the public key. Some of the asymmetric algorithms have this optional characteristic in that if you encrypt with one key, you can decrypt with the other, and the other way around. If you encrypt with key A, you can decrypt with key B. If you encrypt with key B, you can decrypt with key A, but no other key. So the keys are related in a manner that holds. We'll see an example of these in a moment. So some notation. We have two keys now, public and private. So we think of a pair of keys. Public key, in many algorithms, if we want to provide confidentiality or secrecy, we use that in encryption. And we use a private key if we want to provide the same service for decryption. That is, I encrypt with a public key and decrypt with a corresponding private key. And we can use that approach to provide confidentiality. That is, a malicious user, even if they see the ciphertext, cannot decrypt the ciphertext because they don't have the private key. We'll go through an example where we can use them in the opposite direction as well for authentication. First, the public key is public. It's available to everyone, including malicious users. So that's the assumption. but the private key is private, secret. It's secret. Okay? You should be awake and you'll pick up these spelling mistakes. The private key must be kept private, otherwise the system will not work. So we have a pair of keys. User A, we think, has a pair of keys, a public key, often denoted as PU for user A, and the corresponding private key. The keys are related. The different algorithms relate them in different ways. Let's go through how we can perform encryption with public key cryptography and then authentication. Here's an example where by encryption here we want to provide confidentiality. Bob is going to send a message to Alice. Bob doesn't want anyone else to be able to see this message except for Alice. That's the aim here. So what does Bob do? He takes the input message, the plain text, applies some encryption algorithm, and there are different algorithms. We'll go through RSA, but there are others. But some public key cryptography encryption algorithm using the plain text as input and using the destination's public key as the encryption key. So since Bob wants to send to Alice, Alice has a pair of keys, public and private key. Bob uses Alice's public key to encrypt. Everyone knows Alice's public key by definition, including Bob. Bob encrypts with Alice's public key, sends the ciphertext. When Alice receives the ciphertext, she decrypts that ciphertext using her own private key, the other key in the pair. If malicious user Darth intercepts this ciphertext, if the algorithm is strong, if the keys are used properly, Darth has the ciphertext. He knows Alice's public key. He doesn't know Alice's private key. He cannot decrypt. Because to decrypt, you need to use the corresponding private key. And since only Alice knows it, only Alice can decrypt. And hence we have confidentiality. This works if our algorithms are strong, our keys are used correctly, and that we, as we saw, the requirement is that given the public key, someone cannot derive the private key. That must be true. So this is using public key cryptography for confidentiality. Encrypt with the public key, decrypt with the corresponding private key. We can use the keys in the opposite order for a different service. For the service of authentication. Bob wants to send a message to Alice. We don't care about the confidentiality of that message. I don't care if someone else sees it. But Alice wants to be certain that it came from Bob. It didn't come from Darth pretending to be Bob. Okay? So that's our aim here. Authentication. So what Bob does, he encrypts the plain text with his own private key. Has some ciphertext, sends the ciphertext to Alice. Alice decrypts with Bob's public key. If it was encrypted with Bob's private key, it can only be decrypted with his public key. What does this do? This confirms that the message came from Bob. Why? If the message successfully decrypts with Bob's public key, it means that it must have been encrypted with his private key. Because that's the nature of the relationship between the keys. If something's encrypted with a public key, it only decrypts with the corresponding private key. If something's encrypted with a private key, it only decrypts with the corresponding public key. In this case, plain text encrypted with Bob's private key, it will only successfully decrypt with Bob's public key. So if it does successfully decrypt, it means from Alice's perspective, the message she received must have came from Bob, because only Bob has his private key. So Alice is sure that the message came from Bob. And that's an important security service, authentication. What if our malicious user, Darth, intercepted? So Darth receives the ciphertext Y, which is really the encryption of the plaintext X using the private key of Bob. What can Darth do? Darth can decrypt this because Darth has the public key of Bob. We're not trying to provide confidentiality here. We don't care if Darth sees the message. It's not supposed to be secret. So he can decrypt, but that is not useful for Darth in this case. We're not trying to hide the message. We're trying to make sure that Alice is certain it came from Bob. Can Darth pretend to be Bob? No. Because if Darth sends a message to Alice pretending to be Bob, then Darth must encrypt that message with some key. And when Alice receives that, Alice is going to, if she thinks it's from Bob, she's going to decrypt with the public key of Bob. So for the decryption to work, Darth must encrypt using the private key of Bob. But Darth doesn't have the private key of Bob because it's private. Only Bob has it. So this is providing authentication. Of course, someone can see the message. That's not our aim. But no one can send a message saying it's from Bob without the receiver detecting that it's not from Bob. Because no one else has Bob's private key. So this is authentication. And in fact, the concept of a digital signature. Your next homework. You need to send me your homework, and I need to be certain it's from you and not someone pretending to be you and trying to give you a lower mark. That'll be bad. So what do? What do you encrypt with? When you send me the email, what are you going to encrypt with? Anyone? Your private key. So if you want to be sure, or I want to be sure that it came from you, that is authentication. If you send me a message, then you need to encrypt it with your private key. And I will validate that message by decrypting with your public key. So under the assumption that I know your public key. So for the different algorithms, there's ways for creating the public and private keys. They are related, say mathematically related. Once we go through the algorithms, especially RSA, we'll see the relationship. Yes, you can generate a key easily. Yep. In the same way with symmetric key cipher, you can generate a key. Here you just need to generate a key that meets certain requirements, mathematical requirements. And similar, if you wanted to send your message and you didn't want your friends to intercept that, so you send it across the wireless network and you've got your laptop and you capture packets off the wireless network, but if you don't want your friend to see the contents of the message and you send the message to me, what are you going to encrypt with? Which key? Okay. You want to send me a message. You don't want anyone else to see it, the contents. No, we're using asymmetric cipher. You need to encrypt with my public key because only I can decrypt it then, because only I have the corresponding private key. So for authentication, encrypt with your own private key. The other person can authenticate. For confidentiality, encrypt with the other person's, the destination's public key, and only the destination can decrypt then. Yep.
Question with the public key. So let's say Darth intercepts this packet, and in encryption, it is done by the public key, right?
For So this slide here is about providing the service of confidentiality. Remember, confidentiality, make sure no one can see the contents of the message. We want to send X to Alice such that no one else but Alice can see X. So we encrypt it with Alice's public key.
So if Dark, Dark can pretend to be Bob because he can use Bob's public key to
Yes.
send the message out.
In this case, Darth can pretend to be Bob. We're not stopping that. In this case, we're only providing confidentiality. And in this case, we're only providing authentication, not the opposite service. That is, in this case, we don't provide confidentiality, and in the first one, we don't provide authentication. So that two independent services being provided there. If you want both, join them.
You said that the public key and the private key are mathematically related.
Mm-hmm.
What if the attackers, is it possible for attackers to try to find the relationship between the public and the private key since they are
So, yes, we said that the public key and private key are related in some way. That relationship is known. That is, the algorithm for calculating the keys is known. But the algorithm, one requirement of the algorithm must be it is too hard to determine one key from the other. That's a requirement. And we'll see, for example, when we get to RSA, one such algorithm, we'll see that to determine the one key from the other, you need to solve those computationally hard problems that we mentioned at the end of the last topic. That's what they'll rely on. If the attacker could do that, then everything falls down. So try and get your heads around how we use the keys in the different directions for authentication and confidentiality. We can combine them. If you want both services, then you can do both steps in one. That is, we could encrypt with Alice's public key and then encrypt with Bob's private key, both authentication and confidentiality. Some comparison between public key cryptography and symmetric key cryptography, which is also referred to as conventional encryption, the original way. In symmetric key cryptography, sender and receiver must share the algorithm and the key. Public key each sender and receiver must have a pair of matched keys. So we have to have a pair of keys which are related in some way. They're not the same keys. In symmetric key cryptography or conventional encryption, the key must be kept secret. There's just one key, it must be secret between those two users. That's only the case for one of the keys in public key cryptography, the private key. Same requirements here. To decipher a message, it must be impractical to decipher a message without having the key available. And we assume that the attacker or malicious users will know the algorithm. So it should be hard, if you know the algorithm in conventional encryption plus the ciphertext, it should be hard to find the key. Same with public key encryption. If you know the algorithm plus one of the keys and some ciphertext, it should be hard to find the other key, like the question before about. Given one key, it should be hard to get the other key. This diagram is just what we've been through for confidentiality, just a different way to view it. For confidentiality or secrecy, encrypt a message with a public key, decrypt with a corresponding private key, where the pair of keys are owned by the destination. The attacker or cryptanalyst can intercept the ciphertext. They know the public key. their objective is to find the ciphertext or the private key, or the private key. That's their objective. Similar authentication, we do it in the opposite direction. Encrypt with the private key of the source, decrypt with the public key of the source. The attacker's objective is to find the private key of the source. In here, the message is not secret. The attacker can find the message, they want to find the private key. And this is just illustrating how we can combine them together to provide both confidentiality and authentication. Basically, we encrypt twice. Source encrypts the message with the private key of the source for authentication, and then encrypt that with the public key of the destination for confidentiality, and decrypt with the corresponding keys at the receiver. So it's just a combination of the previous two. It's a long day. We have 20 minutes left. Let's go forward a few slides and go through an example of one algorithm that implements public key cryptography. And then we'll come back to this next week. Yeah, we'll come back to that. RSA is one algorithm for public key cryptography, named after Ron Rivest, Shamir and Edelman, RSA, the same guy who created RC4 and other RCs as well. It's the most widely used public key algorithm. There are others, but this is the most popular one. It's a block cipher that takes plain text as input, but the plain text is an integer. Okay? That is, we encrypt an integer and we get ciphertext out, which is also an integer. So if you have a large Word file and you want to encrypt it, then you take the binary form and break it into chunks where each chunk is seen as an integer, some number. Then we encrypt with this algorithm. Let's go through the algorithm with an example. So with the RSA algorithm, we need, as with all public key cryptography algorithms, we need a public key and a private key. Let's, for our example, give you the public and private key. The public key is a pair of numbers, and the private key is a pair of numbers. But only one of those numbers in the private key is actually secret, because the public key is some number, which will say some value E, and some number N. The private key is some other number, D, and the same value of N. That is, these numbers are the same. So really the only thing that's kept secret here is this number here, D, in our example 23. How did I come up with these numbers? We'll cover that later. I cannot choose any number there. There's an algorithm for choosing these keys. Okay? But let's do the encryption first. So this is D, this is E, and these two values are N, referring to our slide. A public key and a private key. We have some plain text. And then we refer to the plain text as M, message. And for our example, our message is the number 88. That's the message we want to send confidentially to the other person. So that can represent a sequence of bits or a block of bits, which could be part of a larger plain text message. How do we encrypt with RSA? Here's the algorithm. It's simply this equation. The ciphertext is the plain text raised to the power of E mod n. Let's do it. M is 88, just an integer. E is in our public key, 7. And N is 187. Can you solve it without your calculator? You could, but I won't force you to do that. So you could expand 88 to the power of 7 into, say, 88 to the power of 2 times 88 to the power of 2 and so on, and solve it manually. If you trust me, the answer is 11. You could use your calculator to solve it if you could do a modulus of a large number. 88 to the power of 7 is 894,432. So that's our encryption. It's very simple. Take our plain text value, raise it to the power of E, where E is the value from the public key, and mod by N, where N is the other value in the public key. Decryption, so now we send the ciphertext 11 to the other side. We have the ciphertext 11, and to decrypt, we take the ciphertext raised to the power of D and mod by N. The same N, a different value here than E. This is D from the private key. So what we've done is encrypted the plain text using the public key. And we're going to decrypt the ciphertext using the private key. Ciphertext is 11, D is 23, mod 187. What's the answer? Okay, 88. It should be anyway. Again, you could expand or use a calculator to find that, but you'll find out that the answer is 88. The question is why? That is, why did we do those two simple modular arithmetic calculations, encrypt one number and take the ciphertext and decrypt using different values, that is D is different from E, and get the original number back? So before we explain that, let's just make sure everyone's clear of all we've done is encryption using a public key and decryption using the private key, where the algorithms are the same. Take our input, raised to the power of E, or raised to the exponent, mod n. Here, when we encrypted, the exponent was E, and the input was the plain text. When we decrypt, the input is the ciphertext, and the exponent is D, for confidentiality. We could do it the other way. That is, if we wanted to provide authentication, I could have taken the message raised to the power of d mod n, and we would have got some ciphertext that we send. The receiver would take that ciphertext raised to the power e mod n, and they'd get the original message back. So we can use this for confidentiality or authentication. Why does it work? Let's go through and explain why it works first, why this mathematically works. That is, why do we get the same answer as the output? And that will lead to the conditions for the key generation. So for any cipher to work, if we take the plain text and encrypt, and then take the ciphertext and decrypt, we must get the original plain text back. Otherwise it doesn't work. Symmetric or asymmetric cipher, that's the same rule. So why does this algorithm give us the original plain text back? Let's look at that first. This is our encryption. And what we did is we took the ciphertext, so that's our decryption equation. M equals c to the power of d mod n. What is c? C is the ciphertext. If we go to here, c is in fact m to the power of e mod n. So let's substitute that in. Let's see, when does this cipher work? That is, for what values of E, N, M and C and D does it hold that if we take some plain text and encrypt and then take the ciphertext and decrypt and get the original plain text? Only some values of these parameters will that work, not all values. In particular, only some values of E, N and D. Which values? C is m to the power of e mod n. Mod. So I'm replacing this c with the equation for how we generated the ciphertext. All mod n. Let's call this, I'll give a subscript, m original, and this is the m, let's call it output, m out. That is, this is the m we start with here, and this is the m we get out after decrypting. If our cipher works, they'll be the same. If they're not the same, it doesn't work. So under what conditions does it work? Let's deal with this side. So we can bring the d inside the brackets here. M to the power of e mod n all to the power of d is the same as m, let's do it, to the power of e to the power of d mod n mod n. All I did is bring this d inside here. M to the power of d all to the power of d, m to the power of e all to the power of d. Using our principles, our rules for modular arithmetic. M to the power of e to the power of d equals m to the power of ed, e times d. Mod n, mod n. But we don't need both because it's the same. 10 mod 20 equals 10. 10 mod 20 mod 20 equals 10. 10, mod 20, mod 20. If we keep modding by the same value, we'll still get the same answer. So we don't need 2 mods here. Sorry, I've missed our original. That is M, which is output from the decryption on the other side, equals M, which is the original input to the encryption, to the power of E times D mod N. We want these two M's to be the same. So the question now becomes, for what values of E, D and N are these two the same? And that will tell us how to derive E, D and N. Any questions so far before we move on to the next step? All we've done is taken our decryption algorithm and then taken C and replaced C with the encryption algorithm. The objective is to find out when does the cipher work. For what values of E, D, N does the cipher work? Well, the values must be such that, since we want we require the original M to be the same as the output M. The plain text in must be the plain text out. So when is this equation true? When does M out, or now we can remove the subscripts. When does M equal M to the power of ED mod N? Anyone got an idea? When does X equal X to the power of something mod N? Sorry? No. Think about the theorems that we've gone through. You go back to your theorems and look at Euler's theorem. I don't have it up here. Yeah, okay. Euler's theorem. What was it? One of the forms. Euler's theorem, one of the forms was saying A to the power of the totient of n plus 1 is equal to A in mod n. Or in other words, A to the power of the totient of n plus 1 mod n equals A. That's what Euler's theorem tells us. And now look at the equation we have on our RSA derivation. We need to know for what values will this be true. Well, the Euler's theorem tells us something about it, because we see, let's replace A with M. M to the power of the totient of n plus 1 mod n equals M. Euler's theorem tells us this is true. Yes. So now equate these two equations. M to the power of ED mod n equals M. M to the power of the totient of n plus 1 mod n equals M. That is, for the equation on that side to be true, ED must be the same as the totient of n plus 1. Is it? Because this exponent here is the only difference from this equation, which is the totient of n plus 1. So from that equation on the left-hand side, if ED equals the totient of n plus 1, then that equation on the left-hand side will be true, and our RSA algorithm will work. Because we will take our input m, our original m, encrypt, decrypt, and we'll get an m out, which is the same as the original m. And that tells us how to generate our public-private key pair. How long have we got? No time. Good. Let's stop there. We'll continue and finish that step next week and go back to some of the slides that we've missed on RSA and so on and go through a more detailed example of key generation.